Calibration is fundamentally a search problem where we are looking for the exact set of model parameters that minimizes the distance between our model's prediction and observed market prices. Mathematically, we frame this as a nonlinear least squares. The catch is that because our function is nonlinear, the contour map isn't a simple smooth ball. It is distorted, featuring elongated troughs, steep cliffs, and flat plateaus. So to navigate this, our starting engine is the Gauss-Newton approximation. Gauss-Newton simplifies the problem by assuming the local topography is a perfect quadratic ball. By using a first-order Taylor approximation and calculating the slope with the Jacobian matrix, the algorithm attempts to leap directly to the bottom in a single jump. However, this creates an illusion of linearity, as Kenneth Levenberg noted in 1944. If our new parameters are not close to the initial values, ignoring second and higher order terms can invalidate the process. Instead of landing at the bottom, this blind leap can result in a massive overshoot, actually giving rise to a larger error than what we started with. So, the solution: overshoot is a masterpiece of classical optimization, damped least squares. So the key insight from the Levenberg and Marquardt was that we must introduce a dynamic braking system. We have to limit the absolute values of our parameter increments so we don't overshoot the specific region where our Taylor approximation is actually valid. Now let's look at the anatomy of this updated rule. We start with the Gauss-Newton core, AT times T times A, which wants to leap directly to the bottom using first derivative. We have also the gradient, this one, pointing straight downhill, but the magic happens with the addition of this damping factor and the identity matrix. The identity matrix acts as an anchor, rotating this step direction, while lambda serves as the master orchestrator, a dynamic scalar that controls both the size and the direction of our step. Now think of this lambda as a dial that morphs the math. When the fog clears and the bottom of the valley is in sight, a lambda approaches zero. The matrix is dominated by Gauss-Newton, giving us fast, aggressive, quadratic convergence. Conversely, when the topography is chaotic, we turn lambda upward towards infinity. The algorithm shifts into pure gradient descent, taking slow, cautious, tiny steps straight to the slope. So, the algorithm interpolation matrix, this creates a perfect interpolation matrix. Gauss-Newton leaps when the surface is smooth, gradient descent crawls when standing on a severe cliff, and Levenberg dynamically adapts between leaping and crawling to successfully navigate highly nonlinear error surfaces. So this synthesis is incredibly elegant, but there is a catch. This entire orchestration relies on one massive assumption, which is that calculating the Jacobian matrix, which is the matrix of derivatives, is computationally cheap. But of course, this brings us to the modern complication. Historically, with models like the Black-Scholes, calculating those derivatives was instantaneous because you just plug the numbers into closed form equation. But with modern, highly accurate frameworks like the rough Bergomi model, We rely on power law kernels and fractional Brownian motion to capture the term structure of volatility. As a result, there is no closed form math. Evaluating the function requires massive Monte Carlo simulation. So we now face the tyranny of the function call. Because there are no analytical derivatives, the Jacobian must be approximated using finite differences, meaning we have to bump each parameter and reevaluate the model. Each single evaluation requires simulating tens of thousands of Volterra paths across hundreds of time steps. Suddenly, a single step in our Levenberg-Marquardt algorithm requires millions of simulated paths. This obviously creates the nested loop of doom. For every single iteration of Levenberg algorithm, the finite difference gear must turn multiple times, and for every one of those turns, the Monte Carlo pricing loop spins hundreds of thousands of times. So one algorithm iteration equals one massive Monte Carlo call, meaning our classical masterpiece has hit a physical low. So how do we fix this? We cannot make the Monte Carlo simulation faster, and we cannot make the Levenberg algorithm require fewer derivatives. The only solution is to stop walking the topography altogether. Here enters the deep learning. We bypass the valley by replacing iterations with inference. So, comparing the two approaches highlights the dramatic shift. The classical path is a slow, recursive loop of guessing parameters, running Monte Carlo, calculating the Jacobian, updating the lambda, and repeating. So the process can take hours. The neural network approach acts as a wormhole. We pass market data through forward pass and get calibrated parameters in milliseconds. So here's how we learned that topography. In step 1, we run massive Monte Carlo simulations offline to generate millions of data pairs, paying the computational cost just once. In step 2, we train the deep neural network on this dataset so it memorizes the exact inverse mapping of the error surface. Finally, in step 3, when live market data arrives, we bypass finite differences completely. So the neural network maps the data directly to the parameters in a single instant inference map. So to summarize, the evolution of this optimization in 1944 and 1963, the Levenberg and Marquardt solved the mathematical problem of navigating nonlinear topography, giving us a masterpiece of analytical optimization. Around 2015, rough volatility models broke that classical iterative loop by introducing a massive computational wall. Today, neural networks don't replace the math, they bypass the bottleneck. We separate the heavy lifting of evaluating the model from the act of finding the minimum. We no longer navigate the fog one step at a time. We map the entire terrain and leap directly to the destination.